Very welcome. All right, so before we start diving deep into internals of defense evasion tactics, techniques, and procedures, let's start from the blank page and ask ourselves, why? Why we should care? Why we should focus on this particular tactic? There are quite a few according to MITRE attack framework. Well, in order to answer this question, let's first define the scope. So, according to MITRE attack framework, enterprise matrix, this is the definition of defense evasion. However, if we take a look at ICS matrix, we get slightly different details. What's common between them is that here, adversary is trying to avoid security defenses, which means our security defenses has to be in place. If they're not, there is no problem. You just get initial access immediately, and you are fully set. Once we have this idea in mind, our next question is, OK, in this case, how it looks right now? There are lots of historical examples. Threats keep evolving. How exactly it looks in 2022, 2023? So let's try to answer this question today. First of all, let's start from Mirai. It was a great example which featured lots of classic anti-reverse engineering techniques. And secondly, because the source code became publicly available by its author, lots and lots of different malware families incorporated little bits and pieces of it into their source code base. So, diving deep here, we can see that lots and lots of particular interesting techniques could be found there. First of all, when we talk about decoding files, obfuscating files or information, techniques, everything which provides value for incident responders, for security researchers of various kind, is actually encrypted. It's encrypted at the source code level. The author provided a standalone tool in order to generate such lines. And the most actionable information like CNCs, credentials, everything is encrypted. The author kindly provided us in comments what their decrypted entry would look like, but of course you will not have them in actual assembly once you start the analysis. What else? Looking here, we can see that the same key is being used everywhere. So why it's important? It means that exactly there is no salt, nothing. So which means that if you're using the same key against the same plain text, the same ciphertext will appear in the end. Second important point is that each string is decrypted on demand just before being used, which means there is no easy way to get all of them at once. You have to apply certain techniques like scripting in order to be able to quickly navigate and analyze the data later. What else? If we take a look at the algorithm very carefully, we can see that it's not ideal. In fact, this is actually a very clear example how encryption should not be implemented. You can see here that the key consists of 4 bytes, and the XOR algorithm is applied against each of them sequentially. For those of you who remember basics of cryptography, it's actually equal to single byte encryption. The key, which we're XORing our data against, is just a XOR of key 1, key 2, key 3, and key 4 bytes, which is extremely insecure, and there are lots of signatures that would catch this behavior and the data actually that lies underneath. Even Yara provides keywords to make detections extremely easy for such use cases. Apart from that, there were other techniques that were used to make both researchers and competitors' life more difficult. So going further, we can see that the argument 0, which is actually the name of the thread, was attempted to be modified. Also, the process name was attempted to be changed by using PRCTL syscall with this particular argument. Now, lots and lots of malware families also incorporated this trick just to make sure that they stay below the radar as long as possible. Finally, when we talk about impaired defenses, the author made sure that, first of all, it becomes more difficult for the operator to connect to the compromised instance and fix it by killing telnet and SSH ports, and also port 80 for web interface. And on top of that, they are creating a fake listener in order to prevent it from being restarted again easily. This is it. This was Mirai. Now, apart from that, there are lots of prominent botnets. Mirai wasn't the first one. It was the most loud example, but in fact, there were quite a few interesting botnets before and after it that didn't borrow its source code. And they also feature certain techniques which we should be aware of in order to make sure our detections remain solid and adequate. So first of all, ptrace. This is a very common anti-debugging technique where this syscall can be used for two different purposes. It can be used to detect the debugger attached to the process. In this particular case, malware can behave differently. And secondly, by keeping this call up and running, we can attach to ourselves, which means it will prevent other security researchers' tools from doing the same, and this way prevent our solutions from detected if we apply certain dynamic analysis. Next one, searching for honeypot details. This is relatively new and not common scenario, but some honeypots recently started checking if their samples end up on honeypots. There are so many of them available in the internet, so security researchers use them more often to keep track of all the trends and new variations of existing botnets. Cori is a great example. It supports SSH and Telnet protocols. Same one has been targeted by Mirai and its recent clones. So again, in this particular case, malware can behave differently, whether it found itself in a more plausible environment or in something that looks like, obviously, honeypot. Searching for VMs. This technique is not common at all, just because there are so many virtual instances these days available in the internet, running on virtual machines, in the cloud. And for malware, it doesn't matter, as long as the goal of the author is just to expand its botnet as much as possible. In many cases, they don't really care whether they end up on a real physical appliance or virtual machine. But we still see botnets that implement this feature by using various techniques, by parsing dim message output, by looking at proc CPU info data. One more way how to make our life more complicated. Searching for debugging tools. This is a very easy technique. You just get a list of running processes, and if you see something like GDB or anything which is not supposed to be found on a generic router, red flag straight away. Finally, this technique is anti-debugging technique. Basically, it's a follow-up for the very first one. In order to bypass this self-attachment technique, the way researchers may address it is by using this particular environmental variable and redefine PRCTL logic, which would allow them to bypass it and make sure they are able to connect to the process and perform dynamic analysis. This environmental variable is not supposed to be present in most cases, so very easy check for attackers to perform and differentiate between fake and real environment. Finally, packers. I'm going to talk a bit more and give you more examples of it, but this is also becomes possibility in IoT environment. Now, let's talk about recent trends, what we see these days, how exactly they look like. This presentation summarizes lots of different research performed by threat intelligence team over the past few months. So it represents actual trends that we see right now, hitting the wire. Most of samples here we intercept using a chain of our IoT honeypots spread across the globe. So this is not academic use cases, but real case in the wild scenarios. So modification of existing encryption algorithms. We already took a look at Mirai in order to refresh our memory and remind ourselves how encryption should not be done. People who borrow Mirai's code can go even further and make it even less secure. In this particular case, we can compare the logic of original Mirai, which had a function called table init, and eventually every individual string was encrypted on demand. It works greatly in production, but it's quite hard to debug. In this particular case, people who borrowed the code decided to make their life more easy, and they decided why bother? Let's decrypt everything in a single routine. And this is what they did. So they introduced a new function, XOR which in a single go will make all strings immediately available for malware and for researchers. We tracked a few different campaigns based on the different hard-coded passwords used for this particular operations. And again, in some cases, we intercepted more samples attributed to a particular campaign. In some cases, less. The algorithm was exactly the same. So here's a link where you can get more information in case you're interested. Next one, ELF header modifications. What it's about? In IoT, the most common executable format is obviously ELF. And despite the architecture, yeah, x86, 32, 64-bit, ARM, MIPS, PowerPC, Spark, SH4, Motorola, anything. In the end, it will be ELF. And here, attackers are trying to play with certain fields within the ELF header, which are not strictly checked by the loader. Basically, they're part of the specification, but they're not strictly enforced by Linux loader, and modifying them can break certain tools, but samples will remain perfectly executable. This is an example which we saw last year being used against samples, which we intercepted. Here, 3 different fields. Start of section header table, number of entries within this section header table, and index of section header table where we store section names. All of them were changed. In this particular case, they were replaced with FF, hard-coded word. And we believe that the tool which attackers used is actually publicly available. It was part of the article released a few years ago. Why? Because actually some of these fields are not word size. They are dword size. But in this particular case, attackers just blindly copy-pasted the code and applied only 2 bytes in order to replace the values of interest. What was the impact? So, taking a look at the most recent versions of very common reverse engineering tools, we can see that the latest version of IDA can swallow it, but it shows some warnings. OK, we can live with it. Hue, Hacker's View, another very common tool, it just crashes still. 2022, no luck. Another problem was with automation. If we want to perform certain automation against these samples and parse them using our beautiful Python scripts, we have a problem because one of very common Python libraries, PELF tools, was not able to process these samples. We submitted pull request for the authors to review it, and we're trying to agree on the scope, convincing them that even though the number of such files is small, it prevents cybersecurity community from analyzing the samples. For now, we have to switch to a different library. But at least this way, we can make sure that future generations of cybersecurity researchers won't be impacted by the same problems. Looking at the data, we took a look at about 700 samples, which we collected over a fixed period of time, and we noticed that about 1% of them was affected by these modifications. Not much, 1%, but probably you don't want this 1% to penetrate your particular network. So it's important to keep an eye on such trends. Apart from that, there are actually a few other ELF corruption options available to the attackers, which are pretty well known, documented. You can find publicly available YARA rules that detect them. We didn't see any of them being applied in the wild as of now. So we keep an eye on it. And again, if you're interested, you can get more information by following this link. Moving on. Intentional functionality downgrading. What it's about? If you start thinking, usually source code goes from small size to bigger size, yeah? People keep adding new features, people keep introducing new logic, new functionality. Not always. If we take a look at another great example of malware family whose source code became publicly available, GovGuild, also known as Torlus or Bashlight, has so many names. It was leaked. It was released or leaked even before Mirai source code. On the left, you can see the original version. You can see lots of different commands supported by it. So based on different protocols they can try to simulate when performing distributed denial of service attacks. So much functionality. And look on the right, this was a small clone of this project, but the author stripped lots and lots of functionality. They didn't even bother adding more data and more code into it. Instead, they kept bare minimum, which allows them to stay below the radar and break all the signatures that would rely on presence of a few of these commands. Very easy, very cheap to do, very efficient. The size decreases, and this is one way how it can be done. So again, if you are interested in more examples, here is a link for you to explore. What else have we seen? glupteba. It's not exactly OT, IoT threat. If you look carefully at history, actually it's a very common pay-per-install framework, which actually works by providing software as a service functionality to other hackers and allows them to deploy their models on compromised networks. However, several models which have been distributed by it were aimed at exploiting IoT vulnerabilities of very well-known IoT vendors. So this was the main reason why we started exploring this particular topic. For those of you who don't know, the recent versions of glupteba implement a very interesting technique in order to improve their resilience. In particular, the CNC information is not hard-coded. Moreover, it's not obtained dynamically from peers or from some other place, from darknet. No, it's publicly available in Bitcoin blockchain. The protocol has a particular opcode, OP return, that allows anybody to store up to 80 bytes as part of Bitcoin transactions, and this space is more than enough to store CNC information. That's what glupteba authors are doing in this particular case. Here is an example of the source code, how it's implemented, but in short, there are many advantages of why this approach is useful for them. You can't shut down Bitcoin just to shut down glupteba, so resilience is great in this particular case. The data is not available in plain text, so the authors worked to at least make it a bit more challenging for security researchers to hide this information. So originally, AES algorithm was used to encrypt the data stored in the blockchain, and of course, the keys to decrypt it were hard-coded into each individual sample. So if you just see the transaction, unless you have the sample, which is supposed to get use of this data and decrypt it, it's more than challenging to obtain the CNC information. New versions, again, follow the previous approach, and they decided, OK, who cares? The samples are so easily available, we don't want to bother. They switched to a simple XOR algorithm with hard-coded key, and this hard-coded key has been used for a very long time. It still hasn't been changed for a while, just cheese sauce. Again, hard-coded into all the samples that are obtaining encrypted information from the blockchain. We keep an eye on this threat. So in this particular case, we spotted 4 different campaigns over the last few years. And the last one started actually in summer last year. Why it was important finding? Because actually it happened a few months after the takedown by Google. So it was an attempt to shut down glupteba operations, and this finding proved that it wasn't successful, unfortunately. glupteba operators still perform their malicious activities, and the threat is still active. Finally, let's talk about packers in IoT. Unlike Windows, where you have so many commercial and open source projects, for Linux, no. Basically, UPX remains pretty much the only open source packer, free packer that attackers are using to protect their brain children. These are stats from our previous research, which we published and released presented on this stage 1 year ago, and we saw that at that time, the number of samples packed with UPX of any kind was about 20%. Here, I'm talking about executables only, of course, excluding scripts and other similar ways how malware can be distributed. And of course, there were different versions of it used across the time. Mostly recent versions of UPX3, and on top of that, UPX4. UPX4 at the time wasn't released, so attackers use their pre-release kind of debug version of it, which broke lots of automation just because in production people use the most recent release build and it couldn't handle version 4. Now it's in the history, so version 4 became finally publicly available with lots of new changes, functionality, and support for new platforms. Mainly 64-bit became better supported, so this was great. However, it's very easy to unpack UPX. You take the tool from GitHub, you run it, and boom, the attacker is defeated. In order to handle this situation, attackers do certain modifications, which, again, similar to ELF modifications that we took a look at before, try to not cross the borderline where the sample becomes fully corrupted, so it still remains executable, but it's modified enough so that original UPX tool cannot handle them anymore. This is a very common approach. There are quite a few scripts available in the internet that try to address it, some particular technique that can be used, or by focusing on particular malware families. So in many cases, malware families have particular ways how they replace hard-coded UPX values with their own signatures, and the scripts are focusing on finding them and replacing back. We believe there is a better way. So here I'm very glad to introduce a new UPX fixing tool. It has been developed by our threat intelligence team, and it has lots of advantages over all previous solutions. So first of all, it's open source, of course, very generous license, so please feel free to try and give us feedback, anything you want to add. It supports multiple architectures, not only x86, but also ARM, MIPS, and PowerPC, and we plan to add more in the future. And it covers all possible UPX corruption techniques that we spotted in the wild over the past 2 years, which I'm not going to cover again, but these are the core examples of them. So changing LMagic value, which is a very famous UPX exclamation mark, been replaced by whatever. In this case, the tool doesn't care. It will spot it immediately. The file and the block size within another structure, and also least common overlay bytes. So again, after running it, you get samples which should be just easily and nicely unpacked using standard UPX tool. So far, it never failed in our particular use case over all the samples we collect from honeypots. We decided to run some statistics, calculate some statistics, and check their performance. So out of 2,100 approximately ELF samples which we collected recently, we noticed that now not 20, but 33% of them were packed with UPX. So despite the fact that UPX still becomes pretty much the only solution and it's well known to security researchers, attackers now use it more and more often. And in this particular case, about 4% of them was corrupted. So if you try to unpack it using standard UPX tool, you would fail. After running this tool, all of them become perfectly unpackable. So you can find more details about this research. And again, please give it a try. You'll be very welcome. OK, to summarize, cybersecurity is a journey, and we're all together here. So attackers keep evolving every day. And as one of my favorite writers, Lewis Carroll, said, we have to run as fast as we can if we want to stay at the same in place. So if you want to move on, you have to run twice faster than that. So constant monitoring is very important. We don't want our customers or anybody else on this planet to be attacked by a threat which we didn't know about or failed at detecting early enough to provide adequate, solid detections. So it's very important. Not all techniques have to be newer, more advanced, more sophisticated in order to work. As you can see, in many, many cases, attackers just apply changes for the sake of changes, because it will still break signature-based detections, and there are multiple ways how simpler methods can also work in this particular case. Finally, sharing is caring. So by sharing this research on the stage and by sharing source code and knowledge, I believe that together we can achieve more. So thank you very much for being part of it, and open to questions.
The hardest problem to solve with this particular tool, where do you see the roadmap for the open source community for the tool? Is there a future that you're trying to hit? Obviously, you've done a lot of very good work on it right now, but is there a particular future that you're trying to hit to?
Yes, thank you. So here at Nozomi, and it's also my personal belief, is that still in cybersecurity community, companies tend to stash the most critical information. We don't share IOCs when people are in need. We don't share samples. We say something like focus on TTPs, but you need actual samples to join the research, to create more signatures, and to protect people better. So here we believe in a different thing, which are highlighted here, that sharing is caring. You already discovered the threat. There is no need to stash information or stash little bits and pieces of code which could benefit the community. So in this particular case, with this tool, we would be happy to get feedback, to incorporate it, and to make sure that everybody can benefit from it. So basically, it's such a common task. Everybody reinvents the wheel. There is no need to do it. Sharing a simple tool will make everybody's life so much easier. So this is the way.
Do I understand correctly that with the ELF header modification, they're leaving the section tables in, they're just removing it from the ELF header?
Basically, here they are modifying fields within ELF header, which are associated with this section header. But if we read the specification carefully, unlike Windows, where there are just sections, yeah? According to ELF specification, there are sections and segments. Yep. And each of them may have their own permission, so there is a bit of mismatch between them allowed, which attackers use in this particular case.
But they're not stripping the section headers, they're leaving them in the binary.
No, they're working with fields within ELF header, yeah.
Okay. Is there a reason, have you seen samples where attackers are stripping section headers?
Is there any?
Well, when you reconstruct the ELF header, then you can get all the symbols then. Like, what is the goal of that technique, to make it harder to reverse engineer?
The main reason why attackers do it is to break some of the reverse engineering tools. So as I mentioned, Hue doesn't work with them, Python libraries doesn't work with them, so don't work with them. So this is a final goal, to make our life more miserable and prolongate the infection as much as possible. Thank you. In this case, thank you very much.